will be here at noon, so good to know that's coming. Well, without further ado, let me introduce our senior software engineer, Dave Sanderling, doing artificial intelligence talk.
Hello, thank you. Thanks, Kamala. And thanks, Jamie, for that introduction on AI. I feel like that was like a perfect precursor to this. So, as Kamala mentioned, I'm Dave Sanderling, Senior Software Engineer at Learning.com. And when she asked me to come down here to Phoenix, I got really excited because I love talking about AI. But at the same time, I got a little freaked out because, I'm a developer. I don't talk to people, much less in front of people, So, I'm flashing back a little bit to one of the bigger ordeals in my young life, which was the 8th grade spelling bee. Unfortunately, I won first place in my school, so I had to go on to the city one. And then I won that one, and then I had to go on to regional and then state. And luckily, I didn't win that one. I got to stop. So I was like, spelling was one of those things I was weirdly good at, but kind of like an AI, I couldn't have told you what all the words meant. Like, I didn't have this real world connection from the symbols to, this underlying meaning. And I feel like that might be why I'm into AI, is I kind of relate to it in some way. Like, as a young kid, I could like read backwards, and I was really good at symbolic things like reading music. Learning new languages was relatively easy for me, etc. But lest this talk on neural networks becomes a talk on neurodivergence, I should probably move on. So, little outline. I'm going to do kind of a quick brush through history and philosophy of AI before we get to the real kind of nuts and bolts of how ChatGPT works, starting with basic ideas of neural networks. And Jamie did a pretty thorough talk on like uses in the classroom, so I might just do a really quick scrape through that. But there's a little bit of math that I kind of fudged through. Anybody in here have a math degree? Okay, good, I'm safe. All right. So let's start with the history. So I could have picked anyone to start with, but I went with this guy because he had the best hair. Gottfried Leibniz. It just looks like his brains are like spilling out of his head. But so he's kind of seen as the godfather of computer science. He believed that all human reasoning could be reduced to like kind of like instruction level logic. And so he and I think Descartes was kind of on the same page as him. They had this idea of like they called it the characteristica universalis, which was like, they thought if you could like reduce all of these sort of sloppy natural language things into instructions, then philosophers would never have to argue anymore. They'd be able to get together and go, let us calculate. Side note, he did not believe that human consciousness could, or that consciousness at all could ever be housed in like machinery. So he thought that the soul or consciousness was something kind of like this separate thing. Thomas Hobbes, around the same time, he thought that he was a materialist, so he believed that consciousness is like just in our bodies. So he would have been sort of a precursor to what we call the strong AI camp, which says that a machine could be conscious. Frankenstein's monster in 1818 famously said, "Fire bad." Just kidding, that was a couple hundred years later on SNL, but I threw him in here to illustrate that even 200 years ago in pop culture and literature, people were wrestling with ideas of like ethics of, what if we create this intelligent being? Is it safe for our kids? I've never read the book, but I've seen a picture. He's like talking to a little girl, and people are like, no. So that's, yes, that's all on Frankenstein. And then fast forwarding to the 20th century, in Hollywood, we start seeing robots everywhere. People are thinking about this stuff. Metropolis was maybe one of the first ones, German movie from, I think, the 20s. Really cool movie. And then we have stuff like HAL from 2001. Data from Star Trek, who was practically human, but there was all those episodes about like he didn't know what feelings and emotions were. I thought that was really cool. C-3PO from Star Wars was basically a walking large language model, right? And then there's kind of the scarier ones like the Matrix, where the machines have taken over and humans are enslaved, or Terminator, that kind of stuff. So fast forwarding to the kind of real, when computers actually got built. Nothing like a military budget to get things going. So around the 40s and 50s, people started building these huge machines. This one was called the ENIAC. I forget what it stands for, but I love these pictures of these gigantic computers that basically now, your iPhone is more powerful than. Around the same time, neurology was sort of a burgeoning field, and people were thinking like, okay, we kind of have this basic understanding of how brains work. Why don't we make computers think like brains and use that to our advantage? I threw in this picture too of the IBM 702. I think this was the one that was on display at a street level picture window on Madison Avenue in New York for a little while. So this stuff was getting like big in pop culture. So at that same time in the 50s, I think it was 1956, there was a lot of funding put into sort of a think tank at Dartmouth University where people said like, hey, let's actually do this AI thing. So I want to kind of point out that early AI didn't have learning so much. It was like pretty much everything had to be like programmed into the computer, like all the logical stuff. So like early language, this is an example of what they call a semantic network. And this is just a tiny piece of what you'd have to teach an AI for it to understand like contextual things about the world. So like, a whale lives in water, is a mammal, bear is a mammal, has fur, all these things. And people actually built out these huge databases of stuff. And it's different now with neural networks that actually just can scour the internet and learn, and we have the processing power for that. We don't have to actually program in all this stuff. But like back then, there was things like chess playing machines that, but they had to have all the rules programmed in, like, if there's a bishop here and the queen's here, then do this, but if this, then done. And, other little sort of toy problems, like one of the early famous ones was kind of like a pre-Roomba little turtle that would crawl around, and when its batteries ran out, it would go plug itself into the wall. So a lot of stuff like that wasn't that interesting, but got people excited. In the 70s and 80s, they had what they call like the first AI winter. People kind of started to realize like it's not working as well as we thought. Real world problems are harder than these sort of lab toy problems that we got excited about at first. And we don't really have the computer power we need to like approximate what the brain is doing. So funding kind of dried up a little bit. People realized like computers don't have the common sense that we as humans have, who grew up with 5+ senses in the world. But at the same time, especially in the private sector, a lot of companies were building like expert systems, speech recognition, robotics, kind of more specialized things. As a kid, my dad worked at IBM, and he worked in a boring little office, but at lunch I would beg him to take me to where the robots were. And I was always a little disappointed that they weren't like R2-D2 or whatever. They were just these big arms that kind of moved around, but it was still pretty cool. So around that same time, in the 90s, I went to college. I double majored in computer science and psychology. And my sort of goal was to like bridge the gap between the two fields. So in psych, I was taking like the cognitive classes, which is all about, how does the brain work like a computer? And then on the CS side, I was taking the AI classes, which is how can we make computers work like brains. And there's only so much you can do as an undergrad with your couple of electives, but I still got to write an interesting paper or two. I still have this book, The Emperor's New Mind. It was one of my favorites, by Roger Penrose. It's kind of about can consciousness possibly be an algorithm, and he doesn't think so. He thinks there's all this quantum mechanics stuff happening, and so computers being anywhere near that are a long way off. But anyway, in college I was really into that stuff, and in fact, separate topic, but I'm still super into what is consciousness, and one of my biggest hobbies is meditation. I've probably meditated thousands of hours since those days, but that's a different topic, different talk. So let's move on into a little bit of the philosophy, which is what this book kind of got me into. So any questions so far, by the way? I wanted to mention any time along the way, if I'm going too fast, please stop me. So probably the two main camps that are still, there's still people arguing about this all the time, strong AI and weak AI. So strong AI would be like Thomas Hobbes that I mentioned earlier, basically saying there's nothing special about our brains, machines can someday possibly be conscious. And then there's weak AI, which is kind of like Plato, not the gooey stuff, but the philosopher, who said that, as humans, we have access to this other realm of, when you have an aha moment, that's like we're accessing this other thing that's not logical computation, and computers can never have that. The names strong and weak are kind of misleading. So weak AI isn't saying that AI will never do useful things. It'll be just as useful, it just won't be the same as us. Okay, so the Chinese room thought experiment. This was thought of by John Searle in 1980. So he was a weak AI proponent, and he said, so he didn't speak Chinese, or probably would be called the Mandarin or Cantonese room these days, but so he called it the Chinese room. So he would say, I don't speak any Chinese, but if you put me in a room with two slots, a slot on either wall, and if Chinese people fed me Chinese characters through the wall, and I had this rule book with all these instructions on what to do when I get this character, how to write this, basically a program. And then if I fed that into the output slot, people outside of the room would think, whoever's in there understands Chinese, but I don't understand any. And so this was his argument that a computer is exactly the same. It's only ever following a program. And no matter how complex it is, there's no understanding or consciousness going on in there. So the strong and weak AI, there's all kinds of variations and refutations of each other to this day, but in 1950, you've probably heard of this guy, Alan Turing. He came along and he was very polite about it. He said, let's not fight about what it means for a machine to be conscious. Let's kind of have this more pragmatic definition of what artificial intelligence means. So I like his quote. He said, do not wish to give the impression that I think there is no mystery about consciousness. But I do not think these mysteries need to be solved before we can answer the question with which we're concerned. And what is that question? It's probably the same one that teachers have. It's, am I going to be able to tell when my kids use ChatGPT to write their paper? So we now call it the Turing test. I think at the time it was called the imitation game. You've probably heard of it. It's pretty famous. But basically you have an AI in one room and a human in another. And then a second human is talking to both of them over a teleprompter or teletype machine or whatever. And if you can't tell which is the computer, then the computer has passed the Turing test. Back then, I don't think there was anything passing the Turing test. Now you might say ChatGPT does sometimes. And I think there have been some other chatbots along the way that occasionally passed it. But anyway, So that is it on the philosophy stuff. Now we can really dig in to how does ChatGPT work. So, so deep learning. Any questions so far, by the way? Let me do my outline check-in. Okay, so deep learning is it's a subset of AI, and it's where neural networks kind of come into play. So, like I said before, earlier AI didn't have any learning going on, so to speak, but this is where like pattern recognition starts happening. So let's take a look. So this kind of came about from people asking, well, how do our brains learn? We have all these neurons that are connected to each other. There's electrical impulses that one neuron will fire, and it'll maybe not cause the next neuron to fire, depending on whatever, biological stuff I don't understand. But, so this is an artificial neural network. So these are programmed in software. And every neural network now has an input layer and an output layer, and then some number of hidden layers. And the more hidden layers you have, kind of the more complex of a thing it can do, like more complex of a pattern. ChatGPT has a bunch of hidden layers. So in the input side, that's kind of like where if you see a neural network as a calculator, the input is where you're putting in the kind of the question you want solved. It might be pixels of an image, it might be data that you want a pattern to be found in. And then on the output is where you're saying, like, tell me what the answer to this is, or what is the probability that this picture is a cat or a dog, or something like that. Okay, so one example of that might be, let's say you have a neural network you want to train to tell you whether a cardio patient has heart disease. So what you would do is you train it on a large set of data. This is an example. So here, this shows we have 297 rows, which is actually probably a very small data set in terms of real neural networks. You need like thousands and thousands of samples. But so this has 13 columns of data, of input data, and then here is the target column. So this tells, does this one have heart disease? No, yes, yes, no. So what you would do is train the neural network on this, and it would learn to find patterns in these different cardio patients. So we have like age, sex, chest pain, I don't know what all these are, cholesterol, ECG, stuff like that. Yes, okay, moving on. Okay, so what's actually going on in there, and this is where the math happens. Promise it's not hard math, it actually is pretty easy. It's just doing a bunch of fairly simple stuff in parallel. So I'm going to switch sides here to be fair. So every neuron that's connected to neurons in another layer all have connections. So they don't connect to ones in their own layer, they just connect to the next layer. And every connection has what's called a weight. And the weight is just a little number, and it's basically a multiplier. So like if on the left, on the input layer, if you're putting in, age and chest pain, things like that for our heart disease example, it would get multiplied by the weight, and that's sort of how the chance that one is activating the next neuron. And then, so all this like pretty simple algebraic stuff happens in parallel down the line. It's like propagated forward. And then we get to the output layer, and that sort of gives you the final answer. It's usually a probability or something like that. So the way the weights work is through the neural network learning, it might weight some neurons lower than others. So like if on the heart disease data set, if one of those columns was like, what color is your car, or something, something that had nothing to do with heart disease, that neural network would eventually learn, like, okay, this neuron has nothing to do with this pattern. It's gonna end up having a really low weight. So how does it actually learn? Like, how does this happen? Oh, by the way, So I wanted to point out that neural networks are not, just to avoid any confusion, they're not hardware. Although back when they were first invented, this guy, Frank Rosenblatt, every neuron was a little hardware thing, and they were all wired together. And he had this cool prediction that eventually neural networks would be able to do this pretty cool stuff. So these days it's all in software, it's all programmed. There's not like little neurons on a chip or anything like that. Okay, so let's get a little more into, and please stop me anytime, raise your hand if there's any questions. So how do they?
Question,
yes.
Who determines the weight? Is that the programmer, the engineer?
No, so the weights start all randomly set. That's a great question. Who determines the weight was the question. So they all start just randomly set. And then through this sort of training process that I'll get to in the next couple of slides, the weights get sort of tweaked to get towards the correct answer.
Thank you.
Yeah. So here's an example of a network that we would want to train to recognize handwritten characters. So OCR, which we see, when you deposit a check on your phone or, send a letter through the mail, is like robots reading your address and recognizing the letters. So here's an easy sample one of a 8x8 little grid, and they're all black or white, so pretty simple example. So this neural network would have 64 neurons on the input layer, one for each of those pixels. And then it would have 10 neurons on the output layer. So the idea is that each of these would be set to 0, 0, 0, 1, whatever these are. And then on this side, this would be the probability that this number is a 0, the probability that it's a 1, etc. So hopefully for this example, we'd have a high, maybe like a 0.9 on the 5. And maybe for 1, hopefully that'd be a low probability. Maybe this looks a little like a 6, so maybe the 6 would have a little higher probability, but you get the picture. So let me see. And then the number of hidden layers and the number of neurons in the hidden layers, that's all just kind of trial and error stuff that the data science people would do when they're creating this network. They might try training a network and like, okay, this isn't working, we need more hidden layers, or maybe we have too many hidden layers, it's taking too long. So I'm not going to go into all that. That's sort of a whole data science course there. Okay, so this would be a training set for learning how to do the OCR. And so supervised learning is what they call it when you have a big labeled data set. So kind of like that heart disease example, it had all the right answers on it, the yeses and nos. So basically what you're doing for each of those, you're giving the neural network, you give it that one image, like the number 5 we were looking at, and you tell it like, okay, do all your math, propagate it forward. Then when you get to the end, it's going to have some random answer because it started with those random weights, Jamie, like you asked. But then then the program that's training the neural network is going to say, all right, actually that was a 5, so what I want you to do is back propagate the math. So like go backwards back through the neural net. Basically like, it's going to come here and say, oh, you thought that was a 3? No, that was a 5. So what I want you to do is go backwards through the math and readjust the weights so that next time you'll answer a little bit closer to 5 on this one. It only incrementally adjusts the weights because it's better to have it like do it slowly over many iterations. It's kind of like if you told a kid like, no, 2 plus 3 is 5, and then if they like overfit it to that, then it'd be like, oh, well then 3 plus 3 is 5, and 4 plus 3 is 5. It's like, no, just slight iterations on the learning. Also wanted to point out that there's no database. So this is a point of confusion I hear a lot. Like neural networks don't store anything. They don't actually like. I didn't catch your name. You're talking about your art and like.
Yeah.
Yeah. So like when you ask a neural network to write me a rap in the style of Eminem, like it doesn't have a database of M&M stuff. It's just like somehow that's all like stored in all those connections and things. And it's the same with these numbers. Like there's no like storage of the numbers. It's all just in the weights. Those are the only things that a neural network knows. So I think that's where the complexity with like copywriting comes in, because it's like it doesn't really. It's not. There's no info there. You know, you can't look in there and be like, aha, you have this image that you copied. It's just all in the patterns. Okay, so here's another example of, so this would be a neural network that is learning to classify dogs and cats based on two inputs. This might be small and hard to read, but so on the x-axis we have the level of domestication, and on the y-axis we have the size of the animal. So as you can see, the Chihuahua is the most domesticated animal of dogs and cats. And then, so I guess when the more domestic you are, the smaller it can be and still be a dog. Whereas if it's bigger, like a wolf, I think this might be here, it can be bigger but less domesticated. Anyway, so this neural network would have probably two inputs, one for the level of size and one for the level of domestication. And it would have two outputs, probably the probability that this thing's a cat and the probability that it's a dog. So one way to kind of think about how the neural network is representing these is, I like to see it as a point in space that represents like the meaning of that data sample. So let's say, what if we wanted to add a third variable, like how furry is it, or how much does it drool, or you could add more and more variables, and so this would go from a point on a 2D plane to a point in a 3D space, or a point in a 4D space, or many more spaces. And the more spaces this neural network is thinking in, the more kind of nuanced of a meaning it can represent these things in. So like the heart disease example, that had 13 inputs. If all 13 of those inputs mattered for that pattern recognition, then you could think of that neural network as seeing those data points as literal like vectors or points in a 13-dimensional space. Let me see. Okay, yeah, so, and just as to flash forward to ChatGPT a little bit, ChatGPT has a very high dimensional space that it sees its words in. So hold that thought on the idea of like ideas being points in space. So here's a very, very simple example of, so this would be a one-dimensional meaning space. You have fire bad all the way on the left and fire good all the way on the right. So based on the situation, like, if it's a forest fire, that would be all the way on fire bad, right? But if you're like making s'mores or something, that would be fire good. So this would be a one-dimensional meaning space, which, by the way, if your significant other has ever accused you of one-dimensional thinking, now you know what they're talking about. And then I mentioned how like ChatGPT has a much higher dimensional way of representing its ideas. So if you were to map out words, I don't know if these are too small to see, but we have like studying and academic and studies, so I'll spoil it. ChatGPT has more than 12,000 dimensions in its word vector space. And so words that are closer to each other in contextual meaning are closer in that space. Like they're going to have more, in like junior high math, we're used to like XY coordinates, but this is like XY blah 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 to 12,000, And so if I speak of a vector is just like a set of coordinates. So any questions so far? Okay, so a little recap. So a neural network learns to recognize patterns, basically. And the input we give it is usually some sort of vector of data, a matrix of data that represents one sample at a time. And that sample could be the pixel values of an image, kind of like the OCR ones we were looking at. It could be an animal like the cats and dogs, or the heart patient. And so it's kind of like just a calculator. It does that one thing at a time. And I want you to think of the sort of state of the neural network after one input as representing a point in this meaning space. Okay, so those work great for a lot of things. At one point in the last, I don't know, 10, 20 years, people started asking, what about sequential data? So this is where we move towards natural language processing a little bit. People are always wanting to figure out if they can predict the stock market, weather patterns, anything where there's like day after day, and you're like, well, tell me what's going to happen on the 11th day if I give you 10 days of data. Coffee. So the answer to that is recurrent neural networks. So what that is like a neural network that kind of feeds back on itself and has a little memory of the previous time step. So with like let's say take the OCR example, every time you feed it a number, it's like recalculating that one fresh. But if you are giving it a string of words, like in a sentence, you don't want it to forget the previous words. You want it to kind of remember them. So you can see it as a net that feeds back on itself, allowing state information to be persisted across time steps. And the reason I put these up here is because those use RNNs to recognize what you're saying. I didn't want to say them out loud because I didn't want 20 people's smartwatches to be like, yes, may I help you? Okay, so I drew this in my notebook the other day when I was waiting for my kid at their music lesson, but so this is sort of an example of if you were to input a string of words into an RNN. So you'd say hello, and then it would do all its calculations in here. These neurons would all take on values that would sort of represent a point in that meaning space. And then you would, so in an RNN, rather than resetting, it's saying, yes, tell me more, I'm waiting for the next step. So then you would put in my, and then, the my would light up these all slightly differently, and that would move that point a tiny bit in meaning space, etc., on down the line to hello, my name is Dave. And so basically what this RNN is doing is it's encoding a string of words into this point in space. Now I want to point out that this meaning space is language agnostic. So whether you say, hello, my name is Dave, or bonjour, je m'appelle David, or konnichiwa, boku wa Dave desu, like whatever language it's in, it means the same thing. So that point in space is going to be the same. So what if you had an RNN that was trained to decode from this point in space and decode it into a string in another language? So that's actually exactly how Google Translate works. They have a bunch of encoders that take strings in the source language and turn it into a point. Then once you have that point, then you have a bunch of decoder RNNs. And literally you go into the drop down in Google Translate and you're like, okay, I want this in Portuguese instead. And it's just picking a different decoder RNN to decode that point into a string of Portuguese. Okay, and this is kind of just a picture of how that would work, going from English to Spanish. So here we have our RNN, it gives it each time step here. Here's our neural network values. They call it the context vector, the point in space. And it gets passed to the decoder RNN, and it turns into your target language. Getting low on time, so I'm going to speed through a little bit here. Okay, so that was the hard part. So if you've stuck with me, congratulations. now we're going to get to like what was sort of the leap from that to ChatGPT? Like, what really caused this blow up in the last 2 years or so? So also keep in mind that this is already way different than, so remember in old natural language processing, people were like programming in all these grammatical rules and you know, the AIs back then weren't learning for themselves like they do now. But you know, if you think about it, like people aren't born with grammatical rules programmed in, right? You know, like some languages, like English, is a subject, verb, object, right? But Japanese is subject, object, verb, and you know, in English you put the adjective before the noun, but in French you usually put the adjective after the noun. That's just stuff you learn as a kid. So it kind of makes sense to train AIs in the same way. Let's see. Okay, so RNNs did have some cons to them. They were very like computationally expensive. They just took a long time to train because of all that looping. So an easy way to explain it might be, you know, the game of telephone where you whisper down the line, and yeah. So like RNNs are kind of similar, like where you have a message that starts from the beginning, and the longer that line is, the more chance that stuff from the beginning might get a little lost. So, like especially if there's an important word at the beginning of that string, it could kind of get lost towards the end. And the other problem is just, like I said earlier, it takes a long time. You know, each person has to go sequentially. And, you know, computer engineers don't like sequential things. We like things to be in parallel. So, you know, people are like, what if we could just all put all the words in at once? That would be so much better. And remember the backpropagation thing I was talking about, where the neural network had to do the math backwards to like train the weights? With an RNN, it's even worse because it has to backpropagate through every single time step as it's learning. So that took forever, and that's why like ChatGPT didn't exist 10 years ago. So the question obviously was, wouldn't it be nice if we could put that whole sentence in at once, and the word order wouldn't matter so much, and we could use parallel processing? Anybody know what these fancy things are? Any PC gamers in the house? Yes, yeah, those are fans on GPUs. So GPUs are graphics processing units. So basically, so in your computer you have a CPU, which is kind of the central brain, and it like accepts one instruction at a time. So like the user just clicked this thing, open up Outlook, or it's 10 o'clock, give them the reminder, you know, so it's doing one thing at a time. And your CPU might have like 8 cores in it, so it's actually 8 things doing one thing at a time. But the GPU is meant to handle like individual pixels, like all in parallel. So it's doing a bunch of simple math really fast, which sounds like a neural network, right? So people that train neural networks basically buy a bunch of GPUs and string them together, and it's perfect for that sort of parallel matrix math that the neural network has to do. So the answer to what was wrong with the RNN was the transformer. So a team at Google actually invented this new neural network architecture in 2017. And basically, the short of it is that it enables parallel processing. I'm not going to go into all the details. I just thought it just looks cool. But basically, this bit here is the encoder, and this bit is the decoder. And I'm not going to go into all that, but ChatGPT is built on this architecture. So this was my little notebook example, sitting waiting for piano lessons. So hello, my name is would all go in at once, each word vector. And then sort of the trick they used was, what if we put the positional encoding on each word? So once it gets in there, we still know which order the words were in. And then this fancy thing called self-attention that I'll go into in a minute. So if we go back to our telephone example, imagine like everybody whispering at once to the final person. So the way to keep the last person from getting confused would be to have like a timestamp on each word, like this was the first word, this was the second word. And then self-attention is a way for the words to sort of contextually know about each other. So like not every word is going to be as important as the others, and you might not want them to affect where this point in meaning space is going to be as much as the others. An example to illustrate that: even though he was very tired, John decided to finish the chapter. So all these words come in at the same time into this transformer neural network. But like when it's processing the word he, it's able to look forward to every other word and be like, okay, he is probably referencing John in this case. And it does that using basically linear algebra, more math. Here's another example. So I took my cat to the vet. So the word vet has a few different meanings. Like I vetted his slide deck before the presentation, or he's a Vietnam War vet, or obviously veterinarian. So how does the transformer know? Basically, it's looking at where these words, when it's processing that, it compares it to each one, and it's doing basically a dot product of the word vectors. So basically what that does is it finds the vectors that are closest together in this meaning space. And it says, okay, vet and cat are kind of close to each other, therefore let's transform the meaning of this towards that. Now if we put in a different sentence like, I gave my cat to a Vietnam vet, then the self-attention mechanism would be able to say like, oh, Vietnam vet, okay, that probably means that. And it would just kind of know that it means a different thing. Okay, so that's how transformers work. What about the specifics of ChatGPT? So ChatGPT is a gigantic neural network that has 96 hidden layers. It has billions and billions of connections. And the meaning space is over 12,000 dimensions. And they're making new versions of ChatGPT all the time. Like this might have been version 3 that had these statistics, but so don't quote me on that for more modern ones. And it basically trained itself by going out on the internet, and like it would mask out the last word look at the first 50 words and then mask out the 51st, and then say like, okay, that one's the answer. So we didn't have to provide it with a bunch of label data. It would just go through and train itself. And it was specifically trained, ChatGPT in this case, on customer support chat databases and movie dialogues, so that tended to make this one a little sound more like a chatbot. So ChatGPT has a vocabulary of 50,000 words. So the output layer of ChatGPT, if you remember our 0 through 9 on the OCR network, so the output layer on ChatGPT would look something like this, with all those 50,000 words. And for every word that it's predicting, it's going to be like, okay, 0.01 chance that it's this one. And like if the answer is aardvark, it's like, okay, maybe you have a 0.9 on aardvark. And it's just going word by word, telling you the probability of what the next word should be. And they do program some randomness into ChatGPT, so it doesn't give you the same answer every time. I think it picks the top 5 or 10 probability-wise, and then it randomly picks from that. So the input is your string of words that you ask it. For example, late one night a few months ago, I said, oh my God, I forgot to write a tooth fairy letter for my kid, and I need one tonight. Like, and ChatGPT wrote this beautiful, sweet, tear-jerking tooth fairy letter for me, and so that was my input string. And then what it does is it gets the next word and it appends that to your prompt, and then it sends that back through again, and then it gets the next word for that and appends that to the prompt and sends that through again. until it gets a done token, which I'm not exactly sure how it knows when it's done, but okay, so that is ChatGPT. Any questions on that before I kind of wrap up? Okay, so that is all pretty cool, but it's really just a bunch of fast processing. You know, I don't have an opinion really on the whole strong AI versus weak AI thing. I'm not sure about consciousness yet, but I think that ChatGPT, you can kind of see it as basically just a gigantic calculator. This guy, Rodney Brooks, is a well-known robotics researcher, and he's definitely a strong AI guy. He says we need to stop confusing performance with competence. And basically that's just saying, like, you know, these things like language and image generation and stuff like that, these are problems that if you throw enough computation at them, it'll at least look like it knows what it's doing. But as Jamie pointed out, hallucination is a problem. That's what they call it when it just gives a wrong answer. It sounds right, but it's not. So AGI is another term that gets thrown around a lot, artificial general intelligence. And what that means is, so that would be an AI that can do multiple things, like, you know, think of HAL or C3PO. The neural networks we have now are still like a calculator, doing one calculation at a time. All ChatGPT, all these large language models know how to do is predict a word based on an input sequence. AGI would be something that is more like an intelligent agent that can, you know, like if ChatGPT woke up one day and was like, I'm gonna go train myself on a horror movie database, you know, like, there's nothing, it can't do that. So that's all for that. I'm out of time, so I'm going to skip the in the classroom part because Jamie did an amazing job at that. The real short question I was going to ask is, do you think it's cheating? You know, I think it depends on what you're teaching, but we also probably, you know, LLMs aren't going anywhere, so they're going to be a useful tool. I know when search engines came out 20 so years ago, at learning.com, some of our earliest lessons were like, how do you use a search engine wisely? And I'm sure some teachers were like, I don't want my kids going home and asking Jeeves how to do their homework. You know? So it might be something, maybe we want to consider how to teach it well. And then these were just some ideas for how to use it in the classroom, but like, as I said, not going to talk too much on that because Jamie went into that. But I liked this website, ditchthattextbook.com/AI. This guy has all kinds of cool ideas on how you can use it as a teacher. But that's all. Did anybody have any questions on anything? Feel free to come up to me later too. I'm shy, but not that shy.